Rock properties. SIGRA uses one of the most common rock test methods, namely uniaxial testing. This frequently reveals nonlinearity with axial loading. Cyclic loading, as conducted here, shows both nonlinearity and permanent offset between cycles. This can be analysed for the tangent and secant axial Young's modulus of the sample, shown here in the upper left figure. The tangent and secant Poisson's ratio value may be calculated, though these are frequently higher than that would be the case for a sample with some confinement. The permanent strain offset diagram at the base shows deformation of the rock with stress. This can only be derived from cyclic testing. Rock mechanics is based upon models of jointed rock or upon models of continua. Generally, the rock is assumed to behave in an isotropic, linear elastic manner until failure as determined by shear, when it suddenly changes its behavior to one controlled by friction on the sheared surface. This is quite unrealistic. Real rocks seldom behave in this manner. Sedimentary rock never does. SIGRA has developed a triaxial test system to determine the anisotropic and nonlinear properties of rocks. The triaxial test involves fitting a core with strain gauge rosettes, then installing it in a SIGRA's triaxial cell. The sample is fitted with a sleeve, which will be loaded hydraulically to provide a confining stress. The rest of the cell is assembled. This includes an internal piston arrangement to provide axial load without an external loading frame. The load sequence is programmed and the test proceeds automatically. The rock sample is loaded through multiple axial and confining stress states, and its deformation is measured by strain gauges. These measurements are then analysed to yield values of Young's moduli and Poisson's ratio for each stress state. An example of the axial Young's modulus values for a siltstone are shown in the plot. Sedimentary rocks are frequently highly nonlinear, and it is not uncommon to see variations in stiffness change of 1 to 4 within a 20 MPa stress range. As part of the triaxial process, SIGRA can also measure poroelastic behaviour so that the effective stress in rock may be determined. This is achieved through gas injection into the core specimen that is being triaxially loaded. Poroelasticity describes how fluid pressure causes the rock mass to deform. To the left of the above figure, the red wireline cube is deformed by a unit stress to the blue cube. To the right, it shows the same cube that has had fluid injected at a unit pressure. The cube partially recovers its dimension. The poroelastic coefficient is a measure of the fraction of recovery. The poroelastic coefficient is dependent on direction and may be described by a tensor. This is an example of the measurement of the axial poroelastic tensor for a porous sandstone. It is somewhat stress dependent. Other rocks, particularly those containing microfractures, show much more variation in the poroelastic values with stress. The value of poroelasticity is important in petroleum reservoir behaviour. It also affects the way in which internal pressures may lead to failure, as in an outburst of gassy coal or rock. It is quite normal for the stiffness in the direction of the bedding planes to be 1.5 to 3 times that across it. These differences may matter in real design and construction. Another innovation by SIGRA is the hydrostatic test, where a sample of rock is fitted with strain gauges and is then cast in silicone resin. It is then installed in a pressure vessel for hydrostatic loading and is loaded sequentially while the deformation is measured. This test can be used on irregular samples to determine relative stiffnesses in different directions. If one of the values of Young's moduli can be determined by a uniaxial test, then the other moduli and values of Poisson's ratio may be calculated. Here is an example of the axial and transverse Young moduli for an elastically nonlinear and anisotropic rock sample measured using hydrostatic testing. SIGRA also undertakes a suite of other rock tests to determine rock failure behavior. One of these has been derived from the Russian GOST standard. SIGRA has adapted it specifically to test for shear failure transverse to the sample. As such, it is ideally suited to shearing samples along their bedding planes. Samples can be tested at a variety of angles and the failure loads are measured. Here is an example of a Moore Coulomb failure criterion fitted to 5 sample tests from a modified GOST shear test. The test is quick and can be used on short samples. We pay attention to the tensile behaviour of some rocks, as these frequently control goaf or caving behaviour or the nature of rock bursting. This video shows the testing of a rock sample that has been cut transversely across a 61mm core in the form of a 15mm thick biscuit-shaped rock sample. The sample is glued between steel plates and is then loaded. The deformation of the rock sample is measured on either side of the test plates to ensure that loading is evenly applied. This shows an example of the results of a transverse tensile test. It shows fairly even stress versus strain on each side of the specimen. SIGRA also measures the axial tensile strength of core. This may reveal strength and isotropy, such as might be caused by mica on bedding planes. This type of test has direct implications for roof failure underground or the caving behaviour of longwall goafs. It is also important in understanding block caving behaviour. SIGRA also conduct a suite of more standard tests, but have found that more attention to detail is required than is generally provided for in these.